Continuing on with the idea of samples, one topic we need to address is sampling variation. Samples are going to vary. I could go out today and I could randomly sample 100 students at TCC, find their GPAs, and average them together, and I get like a 3.1. I could go out again in a couple weeks, get another random sample of 100 students, probably different students, average their GPAs, and I might get a 3.2 as the average. So samples are going to vary from sample to sample. It's not going to be the same result every time. We need to keep that in mind. Another example, let's suppose we have a very small college for ease, and there are only 8 students enrolled. 6 students have taken statistics, while 2 have not taken statistics. A sample of 4 can lead to very different results. You could have your first sample where all 4 have statistics. In this case, P hat would be 1.00, like 100%. I could take another sample, could randomly select 4 students where 3 have statistics and 1 doesn't. So 3 out of 4, P hat would be 0.75. Sorry, it shouldn't say all, it should just say 3. Here, say 2 have statistics and 2 don't. My P hat would be 0.5, 0.50, or 50%. No, it's not possible to have a scenario where 1 student has statistics and the other 3 don't, because only 2 students in the entire college haven't taken statistics. But we can see from these possibilities that we get different results. These samples vary. P, the population proportion 6 out of 8 is 0.75. So in the first case, we were above P, the population proportion. In the last case, our sample proportion, P hat, was lower than the population proportion. And in this middle case, it was exactly the population proportion. So we need to have some way to take that into account. We can take these samples that we have and begin to form the idea of a sampling distribution. The probability distribution of many or all possible sample proportions, P hats, is known as the sampling distribution. Now, as we saw, the estimator, the statistic P hat, will not always match the population proportion P. However, the mean of the sampling distribution should match the population proportion. P hat can be expected to be close to P if survey methods are done correctly. Essentially, what this is saying is that if we take sample after sample after sample, then we should be able to make a fairly accurate assertion about P. So going back to this very small college, I could take my first random sample of 4 students, and let's just say that it's 0.75 as my P hat. I take another sample of 4 students, I get 0.50 this time. I take another random sample, 0.75, have taken statistics. On my 4th random sample, 100%, all 4 have taken statistics. And we just keep going, sample after sample after sample, making a dot plot here. This will be my sampling distribution. And if I average all of these results together, if I find the mean of 0.50, 0.50, 0.50, 0.75, 0.75, 0.75, so on, all the way up to these three 1.00s, that average of these p-hats should match p. And in this case, they would balance out to be 0.75. These p-hats would match p. P-hat can always be expected to be close to p if those survey methods are done correctly, and that goes back to our measurement bias and our sampling bias. And we can measure that bias mathematically, as it's noted below. The distance between the mean value of the estimator, the center of the sampling distribution, and the population proportion p will give us the bias mathematically. So you just subtract the center of the sampling distribution and the population proportion p. In the cases that we observe, all the sampling will be done for us, so we're going to assume that there's no measurement bias. We're going to check that there was a random sample so we can avoid that sampling bias. And we're going to assume the center of the distribution and the population will be the same, so the bias will be 0.